Kia ora, koutou katoa. Well, the lobby will probably continue for a little minute, but we'll make a start. Welcome to this Resilience Challenge webinar, looking at impact-based severe weather warnings for Aotearoa. Thank you for joining us in the April instalment of our monthly webinar series. I'll start with our karakia, whiti ora, then I'll touch on a few housekeeping things and hand over to the team. Ka mihi te po, rangahau te ao, kia iorangi, kia io whenua. He nā mata o te ariki, ke mata nuku, ke mata rangi. He reira koe e tānei te waiora. Ko nā maungaru o nā awa parawhenua, he re uta ki tai, kia tangaroa e. Ko koe, ko au, ko tā ua nei, whiti ao, whiti ora. Ara mai te toki, haumi e, ui e, taiki e. Today we'll be hearing from 3 researchers in our Weather and Wildfire Research Program. We have Richard Turner from NIWA and Sally Potter and Sarah Harrison from Geohazards. They're going to talk us through the challenges, benefits, models and underpinning data required to implement impact-based severe weather warnings. We'll use the chat function for our Q&A today, so please pop your questions into the chat as we go, and we'll hold the Q&A session with all 3 speakers at the end of the presentation. The presentations should take approximately 45 minutes, so we'll have about 15 minutes or so for Q&A. And with that, I will hand you over to Richard.
Thank you, Delia. While I share my screen here, and beginning, and hopefully you can see the slideshow now. So I'll just introduce myself. I'm Richard Turner. I'm a co-leader of the Weather and Wildfire theme for the Resilience Challenge, along with Sally Potter. And in my speech talk today, I will give just a quick general overview of the Resilience Challenge, and then I'll talk a little bit about the modelling effort that's been going underway. And there's a variety of projects there that I'll briefly touch on. So not a lot of in-depth results. We'll get in sort of giving the general overview, and then we'll pass on to Sally and Sarah, who will drill into a little bit more detail about one of the communication and impact-based warnings projects. I'll also talk a little bit about the aims and structure of the program, a little bit about the design, and as I said, handing over to Sally. So the Resilience Challenge is actually made up of about 10 broad themes, and on the left, we have essentially the hazards, the volcanoes, earthquakes, weather and coastal, and they fall under sort of a multi-hazard risk framework. And on the other side, we have a resilience in practice, where we're looking at policy settings and the like. And there's urban themes, a rural theme, a built environment theme, and also a vision Mātauranga theme as well, which is very important for New Zealand. And the Resilience Challenge, the Weather and Wildfire theme actually has quite strong links with the built environment. There's about 4 projects co-funded, but I'm not really going to deal with those today. We'll talk more about the modelling in my talk. And really the basic aim, certainly from the modelling perspective here, is to create a number of very high resolution physical data sets of weather hazards, and it's not just weather, there's landslide and fire weather as well, from extreme weather events that are that have not at a resolution and quality and a format that haven't typically been easily available to researchers and end users or stakeholders throughout the country, because they might not have necessarily the easiest access to NIWA data sets or the landslide data sets from GNS. And the ones that are going to be created in this project are meant to be publicly available to anyone or any researcher, and we're working on the ways of interfacing those with and delivering to people. And improved resilience will come from effective and appropriate use of these data sets, and the impact of, and their use in impact assessment and decision support tools such as RiskScape, and that's which tends to be the interface between our models and the actual impacts. And essentially our program design, we have three sort of types of big weather hazards that were identified in the engagement phase or the co-creation phase, and a large ex-tropical cyclone impacting the northern part of the North Island was identified as one particular vulnerability for New Zealand. Severe winter storms that might affect electrical grids in the south, and particularly wildfire. Now, wildfire can be anywhere in the country, but the particular area that we're chosen for that is around the lower South Island of Otago, but also there have been some cases in interior Canterbury as well. And we have a sort of a planned stakeholder engagement process throughout the life of the challenge, 5 years. That's actually been a little bit hampered by COVID, and we're trying to kickstart that and the sort of meeting with councils and the like, and this sort of webinar today is an aspect of that. So in terms of the extreme ex-tropical cyclone, we really wanted to model maximum credible events in terms of severity, in terms of the rainfall, the wind, the landslide impacts, coastal storms, storm surge modelling, that storm surges that we get, and we didn't necessarily want to use it from some synthetic point of view, but what we've done is we've taken examples of strong cyclones over the last 5 or 6 years, and we've actually our technique has been to shift the New Zealand landmass in the way so that the areas that we want to get impacted do get impacted, so we can actually, because that is actually what we expect that could happen in the worst case, and there's really we don't think there's any particular reason why a storm should, it's a random element as to why it might, say, miss Auckland or something, or go off to the east. So there is a little climatological gradient in terms of the storm tracks passing a little bit to the east of New Zealand, but all things considered, there's no real reason why Auckland is, say, any less immune than Tauranga. And so part of this work was to, as I said, create data sets when we're going down to hundreds of meters and perhaps even finer scale for if we're looking over the Auckland CBD, and we just want to make those available, and also feed into other projects such as Sally's one. We're looking at the impacts of those and how that can inform better forecasts and getting in wording in such a way as to take action. And there's another project as well which looks at the effect of, say, of these hazards on important sites to Maori. So for the ex-tropical cyclone case, we have 35 scenarios from 5 storms, and now 6 because I've actually added the recent storm Feely that passed by New Zealand about a month ago. Most of the modelling has been done at 1.5 kilometres, but there are several scenarios available at 330 metres. We've also looked at some scenarios with warmer seas to sort of get a little bit of an indication as to what might have happened if that was, say, in a climate future. And this adds significant detail. The 330 metres adds significant detail to the city scale. And we did find, actually did confirm our research has been, did show that the New Zealand landmass actually had little influence on the storm track for the cyclones, but it did actually affect the intensity and development. There was some cases where winds died down when it got over land, but when the centre of the storm passed back over the sea, it re-intensified. There was a couple of interesting cases like that, and I just you'll have the access to the slides. So there's a publication that came out late last year, which has a lot more detail. And here's an example from one of the storms. This is a Cyclone Pam, which happened in about 2016, and we've shifted New Zealand east by about 4 degrees and a little bit to the north. And in this case, there's probably around what we'd think were 50-year return period rainfall event for a lot of the ranges, and on the Coromandel and around Tauranga, and some around Auckland. And what was interesting about this, I just wanted to note, was that the Feely storm, I'm sorry about the colour scale here, but its rainfall pattern, which this was an early forecast, which fortunately didn't occur, but early on in the forecast, it looked like we'd actually have very similar impacts to what this scenario has here that we've simulated when we shifted Pam west, or the New Zealand east. So it just sort of confirms that I think our methodology was pretty good. And the other point of interest is that, you know, the 24-hour accumulations here are about 5 years, but there was a case about a month ago, so the third week of March, where there were very high accumulations in an hour around Auckland, which were about New Zealand records. So similar sort of amounts in very small places, very isolated locations in that event. But it shows you that you know, this is a fairly significant rainfall event that would have happened either for Feely or Pam. So we are sort of capturing the intense rain events when we do these shiftings of the cyclones. And here's an example for Cook, where we're just sort of showing the effect of moving the landmass, and you do actually see that actually the structure and the overall large-scale pattern's probably not too different in terms of, but where it occurs is different, and there are some effects of the land that is when you move the cyclone at one point, the landmass 1.5 degrees to the east, you do tend to get larger amounts. That's because it's probably getting a little bit of orographic effect there as well. And the inset ones are the detail that you'd get from adding the 330 meters. I'll move along because time's going to be running out shortly. Here's an example where we looked at what happens with the sea surface temperature increasing. You get lots more rain in the 4 degree case. And so this is actually, it's quite indicative and quite useful to see these. And we've made all of those scenarios available to Andrea Walter at GNS, and she is currently working on looking at what the landslide impacts for all those events would be. So she's building up a database as well, and so we can sort of see what the impacts are going to be in terms of the landslides, and then what's that going to have on roading and houses and the like. And similarly, from these scenarios, there's a PhD student at the Auckland University, Moise Shah, and he is going to be doing simulations over this central business district with very high resolution CFD models. And also comparing those with a wind tunnel, where it's got a physical model of the Auckland CBD. And there below is a sort of, we have tested out a little bit of this methodology with a very high wind event over the Auckland Harbour Bridge. And there's the, well, we actually managed to, this is actually a forecast, but we actually picked the timing and didn't quite get the extreme magnitude of the wind. So I think the actual peaks were more about here, but we certainly got the spike and a peak using this sort of methodology. But there was a that sort of shows the sort of example we can do of the things we can do, and then you can apply that to a sort of a network model when you have the whole city to see what the implications are for transport. In this case, the bridge was closed for a short time. And then we also have sort of interfacing with one of Liam Witherspoon's built project when looking at flood banks. We've got a lot of these scenarios are going to be run through a very high resolution flood model over the Hauraki Plains, and I'll just move to the next one. Cyprian Bossarelli has been doing this. So should see the animation of the flood. So this is this took a very long time on the supercomputer to generate, but he's running through the scenarios now, and this is the first sort of look at the results that we've been getting. And it's coupled with a storm surge, so that's in the Firth of the Thames. And Liam's project is sort of surveying some of the flood banks, and we want to see where the vulnerabilities might lie. So that's some very, very high resolution resource that's going to be available to people for that area. And then, of course, the Maori sites, these are the purple dots there are the sites that are probably interest or concern for iwi around the Auckland area. And Sylvia Tapaki from Scion is undertaking that research there and working on with the some local iwi on ways of sort of seeing how that the information we can provide can be of use to them in their planning on and how they can protect the sites that are of significance to them. And so that's using, so there we're applying a storm surge model, and we're using some of the work that was done in the America's Cup, where we got a very detailed storm surge modelling around the Auckland area to help with that, and that's coupled to our weather models. And then we have the severe winter storm. Daniel Smith is a PhD student at the University of Auckland, and we're working with Transpower to look at ice loads on lines, and we've developed a data set of models, and Daniel's come up with a icing model, and he's just now in the phase of doing some field work to try to validate and calibrate those models. And here's another example of a publication that's happened to date. And finally, there's a wildfire project with Scion, and they're looking at case studies, but we've actually developed several models for several fires, and that's also currently underway as the fire spread modelling and the smoke dispersal modelling. And there they're looking at surveying the community to see what their awareness is about wildfire, about looking at like evacuation plans, and they're looking at the risk perception, preparedness that they have, and hopefully using that they'll use some of the simulation results to when you would show those to communities, that in turn might have an effect on their risk perception. So that's pretty much it from me. I'm going to hand over now to Sally and Sarah, who will be talking about the impact-based warnings, and certainly in terms of the modelling that we've seen there, which I've presented today, the next phase in terms of looking at the impacts is to run all those. They're in a format that can be run through a risk gate to sort of see like what the impacts might be on transport, business delays, or damage states to buildings or what have you. So we can that can sort of quantify the impacts from these storms, and then that can help inform the impact-based warnings. So that's it from me. So I'll stop sharing and hand over to Sally. Thank you. Sarah, sorry. Sally, no, Sarah. Sally.
Me first. Thanks, Richard. Richard, can you see my screen in presenter mode there?
Yes.
Great, thank you.
You can see it as the
right version?
Yeah, just a bit.
Yeah,
okay.
that's thanks, Sally.
Yep. Cool, thank you. Kia ora koutou, ko Sally Potter tōku ingoa. My name is Sally Potter. I'm a social scientist at GNS Science. Thank you so much for coming along today to hear about us presenting on these impact-based warnings. So far, you've heard about from Richard about what that kind of physical hazard modelling initiatives are through the Resilience to Nature's Challenges Weather and Wildfire program. I'm going to be talking next on impact-based warnings themselves, what they are, how effective are they, and what some of the challenges and benefits are from the institutes that would be perhaps involved in implementing them. And then I'm going to hand over to my colleague Sarah Harrison to talk us through a bit more about that data underpinning impact-based warnings. So why do we need to look at this? Well, early warning systems around the world have identified to be needing to be improved. We're still getting a lot of impacts worldwide from all events, but particularly the hydrometeorological, so weather and flooding events. It's been recognised that the early warning systems need to be more people-centred in order to be more effective. And so the World Meteorological Organization, or WMO, has proposed that impact-based forecasts and warnings would be useful to try and help make warnings a bit more effective. So the driving research questions for us, for Sara and I, are how effective are these impact-based forecasts and warnings, and what do we need to do if we want to implement them here? So a few definitions to start with, so we all know what we're talking about here. Hazard is one of the elements of risk. Hazards are any atmospheric, earth or water related occurrence, the action of which adversely affects or may affect human life, property, the economy, or other aspects of the environment. Impacts can be on the natural, economic, built or social environments and occur as a result of that hazard. Impacts are influenced by the vulnerability of the elements at risk and by the exposure of elements at risk to the hazard and the characteristics of the hazard itself. Vulnerability are the characteristics and circumstances of elements at risk that make them susceptible to damage. So for example, if you have a house with a concrete floor, it's not going to be as damaged by a flood as a house with a wooden floor. So it's those sort of characteristics, and you can also do that on people to see what their capacities and capabilities are, as well as what can make them more vulnerable to the hazard. Exposure is the degree to which elements at risk are exposed to the hazard. And so for an impact-based warnings perspective, this might be whether an asset like a building or a person is located in a floodplain area, for example, or close to the hazard, and also how dynamic can we get that. So people's location depends on the time of the day. So they might be at home at night time and at work during the day in the city. And so if we can try and account for the differences in exposure there, that can be helpful for impact-based warnings too. So putting them together, we've got risk. Risk is the likelihood and consequences or impacts of the hazard. So what are impact-based warnings? Well, if we start at the top there, we've got phenomenon-based warnings. These are our traditional hazard-based warnings. So it's the trigger at which a warning, the threshold at which a warning is triggered. Okay, so a hazard-based warning might be based on something like 100 km/h wind gust, and that would be uniform throughout the country. It takes into account the hazard, like the severity, location, extent, duration, those sort of things, as well as the likelihood of that hazard to occur. If we then start to take into account the vulnerability and to some extent the exposure, we've got impact-based warnings. So this might be where the 100 km/h wind gust, it wouldn't really do much damage at all in Wellington, for example, but it would in Auckland. And so the Auckland threshold would be lower than the Wellington threshold. So as soon as we start taking into account those vulnerabilities, then we've got impact-based warning. If we then become a lot more specific, and particularly for our exposure, so that would be things like, a particular ferry service might be cancelled due to the high wind, or a particular road might be flooded because it always gets flooded, then you can start to put out these impact warnings. And then finally, if we take into account the behaviour of people, then we can have call to action warning. So this is when the actual threshold for triggering the warning is based on what you want people to be doing. Now, more recently, a new definition has come out of impact-oriented warnings. This is a warning that no matter what the threshold is, if it includes impact information or wording in the warning, it's an impact-oriented warning. So these are a lot more achievable because they don't need a lot of underpinning risk modelling and those sort of things to go ahead. So how effective are impact-based warnings? Well, first, what is effective? What do we mean by that? In general, warnings strive to empower people to respond to the hazards in a timely and appropriate manner so that we can try and reduce the overall impacts of the event. So the key thing there is we need to know if people are actually responding to the warnings to say whether or not they are effective. One of the key drivers of behavioural response to warnings is risk perception. So this is how threatened do you feel, how concerned are you, and how possible is it for you to take the actions in the warning. So in order to test how effective these impact-based warnings are in Aotearoa New Zealand, a few years ago we conducted an online survey. The participants all got the same scenario. So it was 7 p.m. on a Monday. You see the following severe weather warning issued from New Zealand's Met Service for the next day for your area. Now, half of the participants received a traditional phenomenon-based warning, and that included the words of the wind gusts of 140 kilometres per hour. And the other half of the sample received a different warning, which had impact words in it, so actually an impact-oriented warning. And so it talked about the impacts, but it didn't have that hazard information in there. We got over 1,300 responses for this study. We asked 4 perception questions to everybody, and that was how easy did you find it to understand the possible effects? How threatened did you feel? How credible do you think the message was, and how concerned did you feel? And that was measured on a Likert scale from strongly agree to strongly disagree. And we asked 10 questions relating to their intended actions. So I've got some examples there. So our findings, first of all, we're looking at that impact-oriented warning were more likely to have a higher sense of threat and concern, and they had a higher understanding of the impacts that were likely to occur in this hypothetical scenario. So this is good news for impact-based warnings. It shows it does influence people's risk perceptions. The credibility of the message, we found no significant difference between the 2 different types of warnings. Looking now at whether the impact-based warning influenced actions. So we found that there was no significant difference between the people who received an impact-based warning versus those who received the more traditional hazard-based warning. So this is in alignment with about half the literature out there on impact-based warnings from around the world. The other half found that impact-based warnings did have a significantly positive difference. So impact-based warnings were more likely to prompt people to say that they were probably going to take action. Most of these studies are in a hypothetical sense, hardly any are in an actual real warning. So this is one of the limitations of the research. We also found that the people who received an impact-based warnings were more likely to try and seek further information as one of their actions, which is quite interesting. So we have to acknowledge here that there are a lot of other factors that are in play when people are deciding whether or not to respond to a warning. The warning message itself is just one of very many factors, with others including things like prior experience, what their gender is and age, whether they thought they were exposed to the hazard and likely to be impacted by it, and what if they've got any plans in place. And it may well be that including guidance messages in the warning is actually far more effective than worrying about what the impacts are. But ideally, probably include all of those different elements. So including that guidance message is super important. I've got my paper reference down the bottom there if anyone wants to find out more about that study. So in a summary there, impact-based warnings, mixed results on how effective they are for the public. So perhaps they could be quite effective for stakeholders though. So in Germany, Thomas Cox and colleagues found that the fire services used that impact information to inform their response, but in a very short time period, about 2 hours as opposed to days in advance of the event. And then in the US, Harrison et al. Found that the emergency managers and media were satisfied with the new impact-based warning products that were issued there. So there's a lot more work that needs to be done in this space. And so we did a New Zealand case study on what our stakeholders thought the challenges and benefits would be of implementing impact-based warnings here. We started with some interviews in Europe and then did 3 workshops in New Zealand with hydrologists, emergency managers in Wellington, and a Met Service workshop. We found that they thought the benefits of impact-based warnings were that the public would have an increased understanding of the impacts. And as I've just shown, that's true. Everybody does seem to have a better understanding of impacts when they receive an impact-based warning. They found that the forecasters were more likely to have more awareness of the antecedent conditions. So by phoning up the local hydrologist and saying, how are the river's looking, we've got this big storm coming, the hydrologist can say, actually, it's really high, saturated ground at the moment. So Met Service might then issue a higher level of warning because it might have more impacts. So that was a perceived benefit there. They thought perhaps there'd be a reduction in false alarms. So this could be true, but I think it needs to be checked. It needs to have some research wrapped around that to see if this is actually true. And they thought it would be a benefit that there'd be an increased interagency communication. Everyone's just going to be talking to each other more and coordinating a lot more, which is beneficial. Some of the challenges identified. The first one is scale. Are impact-based warnings designed at a societal risk and impact level, or are they designed for individuals, so people on the ground? This is a really crucial decision that needs to be made when setting up an impact-based warning, because if you're talking about the level of impact that's happening, if one person, one farmer, for example, is impacted by an event, but they're the only ones, it might, if you've got a societal risk sort of framework wrapped around the system, then they'd only receive a low level of warning because overall it's not very much impact. But to that one farmer, it was probably pretty important to get warned for that event if they were going to be impacted significantly. So a lot more needs to be looked into there. There was a perceived lack of impact data, which is why we've got Sara did her PhD and she'll talk about that next. Warning verification is difficult because if you warn for a highly impactful event and then everybody responds appropriately and mitigates all the impacts and there's no impacts occur, then it's hard to then say that your warning was correct. So that's also something that's being grappled with around the world at the moment. Roles and responsibilities is also a tricky one. It can be quite difficult with the agency's responsibilities if they don't hold the information about vulnerabilities and exposure to be able to incorporate that into their warnings. So perhaps then it should be the likes of civil defence emergency management agencies, but then they don't hold that hazard data in a dynamic sense. So it really comes down to a lot of interagency coordination there, but it needs to be defined whose role this would actually be to issue that warning. There was also a perceived increased burden on agencies from some of the workshop participants. So this is when they might provide Met Service with some information about what the impacts might be, just for Met Service to give the same information back to them essentially. So there was a little bit more that needs to be worked out there as well. And again, the paper is at the bottom of that slide. So in summary, impact-based warnings seem to be effective at influencing risk perceptions, but they're not that effective potentially. There's still a lot of questions around how effective they are at actually promoting a response. But they could be quite useful from an agency perspective. There are several challenges that remain in implementing impact-based warnings, and one of those is the need for more supporting data to try and fulfill the requirements to issue these impact-based warnings. So with that, I'm going to hand over now to Dr. Sara Harrison to talk a little bit more about the data, and I'll be popping back in again at the end of her presentation. Thank you very much.
Hello, sorry, I lost my screen. Cool, I'll start sharing. All right, yeah, thanks, Sally. Good morning, everyone. I'm Sara Harrison, a hazard and risk management scientist at GNS Science, and today I'll be talking to you a little bit about some findings from my PhD thesis, particularly in answering the question, what data do we need to implement impact-based forecasts and warnings? As Sally indicated in her presentation, forecasters and meteorologists often don't possess the knowledge or the data needed to forecast and warn for the impacts. And as one participating meteorologist in my study said, our responsibility is for the forecast of rain until it hits the ground. After that, it is the responsibility of other agencies to deal with what that rain does. So that's a direct quote from an interview with a meteorologist, and that kind of sparked me to look at who actually has this knowledge and this data, and where can we find it and how can we get it and use it. So to answer this question, I used a grounded theory methodology, which is an inductive methodology typically used in social science research for developing ideas and theories from observations. I collected primary qualitative data through interviews and workshops. I interviewed 39 officials from National Meteorological Services, both inside and outside of New Zealand, as well as officials from New Zealand civil defense and emergency management groups and regional councils, as well as risk modelers, people from the public health sector, lifeline sector, agricultural sector, etc. I triangulated the interview results with 3 workshops that I ran with a total of 20 people representing 2 different civil defense and emergency management groups and regional councils, the New Zealand Met Service, and researchers that have expertise and experience in risk and impact modeling and impact warnings in New Zealand. So I started with asking the question, what data do we actually need to implement impact-based forecasts and warnings? And from consulting the literature and discussing with my participants, we identified that hazard, impact, vulnerability, and exposure data are all needed and used through the warning value chain of impact-based forecasts and warnings. The value chain is depicted in the figure on the right, where you can see that primarily hazard data is used at the top for detection, observation, monitoring, creating weather forecasts, and creating hazard forecasts like flood forecasts or landslide forecasts. While vulnerability and exposure come into play in the second half of the value chain, which involves the actual forecasting of the impacts and creating and issuing the impact warnings. I also identified a growing need to forecast and warn for social and health impacts, including the risk of asthma attacks from thunderstorms, and impacts for the agricultural sector from low to medium impact events. We also need to account for antecedent conditions, human response capabilities, and human behavior, which change over space and time. Thus, this creates the need to define thresholds using what we call dynamic exposure and vulnerability, because exposure and vulnerability changes over space and time as humans move about during the day. So the next question that I asked, once we found out where along the chain different data types are needed, where can we actually get the data? So through talking it out with my participants, I tried to identify as many possible sources of hazard, impact, vulnerability, and exposure data as I could in New Zealand. And a whole table, several long tables of the data sources I identified are available in the paper cited at the bottom. This is freely available through open access. But just to summarize, there are a bunch of different sources that I identified, particularly for impact data, which was quite a surprise because, as mentioned, there was this perception that there's not enough impact data. So it seems like there is a lot. It's just a matter of tracking down and determining whether or not it's usable for this purpose. The real gap is in the vulnerability data, as you can see. We need more knowledge about vulnerability in New Zealand. We can get it so far from some vulnerability assessments. We can get it from some asset information, such as the way buildings are designed and built and how resilient they are to certain hazards. We can get it from building damage assessments after an event, also from census data. And tacit knowledge and experience and intuition were identified as a really large kind of knowledge resource or knowledge reservoir, and none of that information is documented, and that's a real risk. When someone leaves their role, switches organizations, or retires, that knowledge can be lost. So that's a real risk that we need to work on. Exposure was surprisingly quite a bit of data sources were identified. In terms of dynamic exposure, though, there's still a need to find out what we can get for kind of real-time exposure data. So population movement via mobile phone data is a potential source, as well as social media. So in terms of where we can actually get the data, so I tried to map out all the different agencies that have these data sets. And I tried to group it based on what type of data it is, if it's hazard, impact, vulnerability, or exposure data. And you can see, like I mentioned, there's quite a gap around who has vulnerability data. But you can see in the middle, there's 4 key agencies or key groups that actually seem to possess quite a bit of all 4 types of data. And those are local and regional councils, researchers from different institutions, NIWA, and GNS Science. And so it's a matter of determining whether or not the data that is in these agencies or held by these people is readily accessible in a format that is usable and useful. And that was one of the key challenges that was identified in my thesis, which was actually whether or not the data is actually interoperable and useful beyond its original purpose for whatever project it was designed or collected for. So if we can actually get the data that we need and we find out that it is useful and usable, how do we actually use it in the impact-based forecasting and warning chain? So for the next few slides, I'm going to focus on the bottom half of the value chain that I showed you earlier, and this will be the impact forecasting components and the impact warning components. So this figure shows the data needs and uses for forecasting impacts. In this component, I identified 2 general approaches to forecasting impacts that use different data in different ways. These are the most, these components are either quantitative or objective model-based approaches, which is shown on the left side, or more qualitative and subjective impact-oriented discussion approaches shown on the right side. Model-based impact forecasting approaches use computer models, algorithms, and quantitative data to identify potential impacts of varying severity. Specifically, risk models require detailed data about the fragility or vulnerability of the assets, including buildings, infrastructure, and people, dynamic exposure, and hazard data. And this is where Richard's work, as well as Andrea Walter's work, and the work of the teams at NIWA and GNS on Riskscape really come into play and can feed into this component. Impact-oriented discussions typically involve many stakeholders that possess the different types of knowledge and information needed to understand and forecast impacts. In New Zealand, the impact forecasting approach tends to be an impact-oriented discussion. For example, the red warnings from the Met Service's new warning system are issued based on impact-oriented discussions with hydrologists and emergency management groups. A red warning doesn't have a fixed threshold. It is only issued if the event is expected to produce significant impacts. The information is used to inform a red warning decision is gathered from directly communicating with the local emergency management groups and regional councils or local councils where the impacts are expected to occur. And then impacts reported in the media and on social media platforms have been used to help verify and update these warnings, which I'll talk about shortly. Next, I identified 3 steps within the impact warning component, which are defining impact thresholds, updating warnings, and verification. So first, hydrometeorological warnings, as Sally mentioned, are based on thresholds traditionally set around physical hazard characteristics, such as this amount of rainfall in this amount of time. Participants in my study indicated that previous event impact data can help determine warning thresholds. For example, investigating the drivers of the resulting impacts from a recent event can help redefine thresholds such that they are specifically impact related. Like the impact forecasting approaches, countries and regions appear to use different approaches to defining impact-based thresholds, varying on how systematic they are. For the more qualitative approaches, tacit knowledge and experience are less systematic ways to identify future event thresholds. New Zealand emergency management groups tend to use tacit knowledge to identify different river level impacts. For example, the Northland Emergency Management Agency works with council hydrologists to informally forecast flood impacts and inform responders and communities. These examples are less systematic than model-based techniques, and participants envisioned using impact data and risk and impact models to classify what is hazardous. Engineers often use impact data to inform the vulnerability function in risk or impact models by associating levels of damage to hazard intensities for a given asset. So post-event damage surveys can be used to develop and calibrate vulnerability functions and identify impact thresholds. Thresholds based on impact data alone are less useful if there's a change in the underlying vulnerability and exposure. So as shown in the bottom of the figure, it's important to incorporate dynamic exposure and vulnerability so that the forecasts and warnings are relevant. The next step I identified in the impact warning component is updating the warnings. And here, real-time or near real-time hazard impact data streaming onto meteorologist screens are highly valuable to participating national meteorological services, as real-time information allows the meteorologist to adjust the warnings on the fly. As you can see in the figure, updating warnings starts from the initial impact warning, which leads to actions taken by the warning audiences or no actions. And these actions can determine what human impacts can occur or no impacts if they took the proper actions. The hazard can change in space and time, also causing different impacts to occur than expected. So warnings can be updated with this real-time information on the fly, and dynamic vulnerability and exposure can also change as impacts unfold and as people take their protective actions. So that also can contribute to updating the warning. The last step in the impact warning component is verification. To continuously improve their services, warning organizations routinely verify and validate models, forecasts, and warnings. Participating National Meteorological Service officials in my study described how warnings have traditionally been verified based on the occurrence of the forecast hazard, with little investigation into what happened on the ground. This verification involves meteorological observations to confirm the occurrence and timing of the hazard in comparison with the forecast and warnings. As you can see in the figure, the impact warnings that were issued lead to certain actions, which then result in impacts or no impacts. These impacts can then be used to verify the warnings that were issued, and the feedback loop from learning from the verification to adjust procedures and impact thresholds is represented by the arrow pointing back to the verification to impact warnings. There are, of course, challenges with verifying impacts. For example, what happens when no impacts are observed because people heeded the warnings and took measures to protect themselves and their properties to avoid the impacts? This is a problem that they've been experiencing in the UK with their impact-based warnings, and a New Zealand meteorologist in my study indicated that verification isn't binary. The New Zealand Met Service meteorologist uses a combination of observational hazard data, impact data from the media reports, and experience in a pragmatic approach to assign a verification score to the warnings. Thus, a multi-factored and multi-data approach grounded in pragmatism and experience presents an alternative to verifying impact forecasts and warnings. So where do we go from here? We've identified, Sally and myself and a team of other international researchers in this field have identified several research gaps and future directions for this. So the first question is, who are impact-based forecasts and warnings meant or aimed for? Who is the audience? And that touches on the question of the scale that Sally mentioned. Where is the value being added by impact-based forecasts and warnings? What do people need, and what is the purpose of the outputs? And what is realistically possible? What is a successful warning, and what is the benchmark for optimal protective action? And finally, we need more in-depth understanding around the decision-making process for both the warning recipients and for the warning issuers. And I will hand it over to Sally. I'll just keep the slides and you can say next slide.
Yep, thanks. Okay, so some of the global initiatives in this area. The World Meteorological Organization's World Weather Research Program has three core projects. One of them is the High Impact Weather Project, and that's I co-chair that with Brian Golding from the UK. So there are four flagship projects underneath this. One is the Value Chain Project. The next is the Citizen Science Project, which is led out of Massey University. And there's Towards the Perfect Warning Springer book, which is just about to come out, so you can keep an eye out for that one. And then the fourth one, which is just getting off the ground, which Sara mentioned, is an impact-based warnings group, which we're going to try and identify what some of these research gaps are by using a couple of virtual workshops later on this year, and try and write up that into a paper or something that can guide what we can look into further and over the next couple of years. And so if you want to know any more information about the High Impact Weather Project, the website is at the bottom there, highweather.net. Thanks, Sara. And so the next question is, there's a lot of progress on impact-based warnings for weather hazards, but could this be translated across to geohazards? Well, we think, yes, there is potential here, particularly in New Zealand, because we have such an awesome risk modelling software in development called Riskscape. So this is where we have those different layers of hazard, exposure, and vulnerability, which combine to have a impact output. So it would say what the likely output impact would be from a particular scenario. And you can run it a lot of times and then make a probabilistic output as well. So we think that we could use these dynamic weather models and also for the different hazards, which I'll get into, overlaid with the exposure and fragility function kind of information to come out with an impact forecast prior to an event. At the moment, there's a lot of work on what the impacts would be from an earthquake in New Zealand. So right after an earthquake, they can run what the shaking was from that event and then produce what the impacts were likely to be from that event that's just happened. There's also a forecast models in development, for example, from earthquake-induced and rainfall-induced landslides, as well as volcanic eruptions, so particularly ashfall forecasts. And you could potentially do this for our earthquake forecasts and tsunami as well, because they're spatial and we just need to have the right asset and fragility function type information in Riskscape ready to run. So I think there is a lot of potential here. Earlier this year, we had ex-tropical cyclone Dovie come down right at the same time as the Hungatonga Hungaha'apai volcanic eruption occurred that caused the tsunami to come to New Zealand. So, for example, in Northland, they had sea surges from both these events occur at the same time, and some of their boaties were affected by this. So the question is, could impact-based warnings have helped? Instead of having warnings from two different agencies and two different sort of hazards coming together, the impacts were pretty much the same for those particular boaties. So is there potential there that we can have impact-based warnings for a targeted audience? That's something that Sara in particular is going to be leading, looking at this kind of thing and how effective that could be. And then the next question is, can crowdsourcing this hazard and impact data in real time contribute to impact-based warnings? So we have another initiative occurring at the moment where we're trying to set up these surveys online that are permanently there, that anyone can come in and log what the what the hazards are that they can observe and what the impacts have been on them. And so then we as scientists get to have that information straight away, and our aim is to have it straight back on the website as in some sort of spatial map so that people can see what their contributions were. And so that's how Felt Rapid works at the moment when you put a Felt report in from an earthquake shaking, but it'd be quite nice to get this for all our hazards in a nice coherent way. So that's something that we're working on as well at the moment. So I think dreams are free, it's a big project, but that's kind of where we're working for at the moment. So I think that's it from us, Sara, isn't it? If you want to go to the next slide, it's just got our email addresses on there if you do want to contact us about impact-based warnings or anything else. We're happy to help, and thanks Deb. But yeah, we can move over to questions, and I've seen that there are a couple on there that I can have a stab at. But I thought, Richard, would you like to just very briefly describe what the benefit is of moving New Zealand's landmass around as opposed to moving kind of the storms, I guess? Thank you.
Yeah, that's basically it's actually easier methodologically to do because you're only dealing with what we call an ancillary file, and that's the landmass. If you start trying to move storm tracks around, then you're moving a whole bunch of boundary conditions. It's just pragmatically a lot easier. Also, the other thing too, in the paper with Ian Bootle and myself and Stuart Moore, we talk about, well, why do you even have to do this approach? Because why can't you just say, here's a storm, you got your rainfall patterns, just move it around? But it actually, the dynamics of the storms aren't quite like that. They do get affected by a little bit by the landmass, even though it's, I said it didn't really matter too much in terms of New Zealand affecting the storms. Actually, it does affect where the rainfall because of their orography, but it also does affect, so to say, depending on the track, whether a storm might weaken and then re-intensify. So pragmatically, it was just a lot easier to do that, and it also added a little bit more. It was a bit dynamically more realistic. And I think there was another question about the Tasman lows. Yes, they're highly significant weather events, and they do deliver a lot of rainfall. But there's probably, well, in terms of, there's a reanalysis project going on at the similar sorts of resolution, and those results will be available in a couple of years, and they will capture many Tasman low events. But reason we did the cyclone one is that you can get some very intense rainfall events over short duration, but they also combine with other hazards such as the very extreme wind gusts as well. So we were trying, and the storm surge. So we were trying to get that multi-hazard, the realistic temporal sequence of wind, rain, and surge is what we were trying to capture. So that's why we tended to focus on the Tasman lows for the Auckland area. And then the last one was from Chris.
Thanks, Richard. I think we've probably only got one more minute. So
all right, I'll let you answer the other ones, and I'll email. I'll type a reply to Chris in the.
Yeah, that'd be great, actually. Yeah, I'll try and cover off a couple of them combined. So we've got questions in there about could impact-based warnings be used for the likes of drought, and I think also climate change in terms of longer-term type warnings. I think maybe, and nobody's looked into it yet. In terms of warnings, it's usually a short fuse warning that we're looking at these kind of behavioural responses. So I think more work would need to be done in this area to see. It could perhaps work for the coastal erosion type scenarios because it's a lot shorter fuse. Potentially if you had a surge coming in or something like that, I think there's definitely potential for impact-based warnings in that kind of situation. In terms of warning fatigue, as I said in my presentation, I think more needs to be done for impact-based warnings and warning fatigue. Brenda, I see you're on here. Brenda Mackey, who's in Australia now, has done work on this in a wildfire sense. Generally, with warning fatigue, we find that people still will respond, even if they've had a lot of warnings come their way, as long as they think that they're under threat. They're still going to evacuate, for example. But there's, of course, a lot of nuances in that which require a bit more time to answer fully. But thanks, Brenda, for putting your email address in there. That's great. Sarah, do you have any final words or questions you're able to answer quickly in there?
No, I just want to note that I've seen Ross Roberts' question about the Lifeline utility services and getting buy-in from them and links with the trifecta reform of the CEDAM Act. I don't have an answer to that question, but I think it's a really important question that we need to keep in mind.
I think it comes back to the interagency partnerships, isn't it, Sarah, and just everyone working together if we want to use that.
Yeah.
Thank you, everyone, very much for coming, and I'm going to hand back over to Delia to close us out.
That's great. Thank you, Sally. Well, we can close by thanking our speakers for sharing their time and research with us today. We'll email a video link to you all soon, along with a short feedback survey. And because we haven't had time to answer all of your questions, we will address those as well by email. So a big ngā mihi nui to you all for attending. We hope you enjoyed this, and look out for our next research webinar, which will be presented by our volcanoes team on the 31st of May. Kia pai tō rā.